Good morning. That's only me. Morning, Mary.
Morning.
Looks like it's just you and me, kid.
It'd be easy.
All right. Well, it's almost 8 o'clock. I'll be getting started in a second.
Okay.
All right, it's 8 o'clock. We're going to get started. All right, so let's see where we're at here. So today, per the table of contents, we're going to go to syllabus. Let's have a look at what we're doing. We're supposed to be at today. All right, so we are Thursday, September 24th. And yeah, it looks like we're a little bit ahead here. So we're going to do introduction to buffers. We'll get started on some buffer stuff here. So the good news is we'll finish early. We'll have plenty of time for review here. All right. So we've already been doing some stuff with buffers, and we did that when we were talking about titration curves. Here we go. And as I've got here on the slide, a buffer is a solution of a weak acid and its conjugate base prepared in such a way that the solution will resist large changes in pH upon addition of small amounts of strong acid or base. Now, this is something that we actually do in the lab. Now, to physically make a buffer, this is how it works.
Professor,
Yes.
I don't know if you can share your screen.
You know what?
I can't see it.
You know what? That's my bad. I cannot believe I did that. Let's try this again. Let's share. There we go. Sorry, I accidentally hit something here and opened it up, and I need to close it in a second. All right. So when we're making a buffer, here's how it works. We have a beaker that's got AH in it, a beaker that's got A- in it, and then we put them both into another beaker. So we have this mixture of AH and A-, where AH is a weak acid and A- is its conjugate base. So remember, in order to get a conjugate base, and we talked about this the other day, conjugate base, whoops, remove H plus from the acid. Simple as that. That's all you have to do. And if we do that, we remove H plus. Let me get rid of this thing that I opened up here, but I didn't mean to open up. All right. And that's our buffer right there. That mixture of AH and A-. And it says here, prepared in such a way, solution will resist large changes in pH upon addition of small amounts of strong acid or base. Now, the rationale behind that, and I'm going to show you the two situations here that we're going to deal with, because this will work for both strong acid and strong base. So if you've got a buffer, and let's say it contains, actually, let me do something a little bit bigger here. And I'm going to shrink this as well. There we go. A typical buffer will contain almost equal amounts of the AH and A minus, but it doesn't have to be exactly equal, but I'm making it equal here. If I add H plus to this, and the H plus is from a strong acid, for example, HCl, then what's going to happen, and if I just add 1 by H plus, then A minus will react with the H plus and become AH. But the whole point here is that the H plus from the HCl is now gone. So we've got AH, 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 AH. And now we've got AH over here, A minus and A minus. So we've lost an A minus and gained an AH. And what's happening here is that the pH only goes down by a little bit, because what we've done is just turned the H plus into another of the weak acid. The weak acid, of course, isn't going to really affect the pH of this solution very much. Will it go down? Yes, it will, because we've done two things. We've gained a little AH and we've lost a little A minus, so the pH will go down a little bit, but not by a huge amount. We can look at the other case as well here. I'm going to show you this in pictorial form in the slides too. So again, we start out with our acid. And our conjugate base to form the buffer. And then we add in OH minus. Now the OH minus could come from a strong base such as sodium hydroxide, like this. And the AH will react with the OH minus. Notice the A minus won't react with the OH minus. That doesn't make any sense. But the AH will react with the OH minus and form A minus plus H2O. So this is already in water. So one of these AHs turns into A minus. But you'll notice that the OH minus is gone completely. And this will mean that the pH will go up by a little bit, because now we've got more A minus and less AH. So that's what basically what a buffer does. And it will only work if you have this mixture in solution. If you just used water, and I've got this here, if I just used water and added HCl to water, I'd expect to see a pH drop of maybe 5 units. Say it might go from 7 down to 2. But if I do H plus to this typical buffer here, where the H plus goes right into the buffer, then the pH might go down by 0.1, 0.2, something like that. So the change in pH is going to be pretty tiny. Does anybody have any questions? You actually do this in the lab as well. So, you'll be actually doing that this week in the lab. So you should be doing that right now, or, looking at the video at least and seeing the effect of this in real time on a pH meter, because we actually do prepare a buffer and add strong acid and strong base to it and look at the differences, what happens to the numbers on the pH scale when we add stuff to buffers, strong acids and strong bases. Okay, anybody any questions? Okay. So this is a typical question that you'll get on a test. And it's going to be something like this. A buffer is made up of equal volumes. Now it's going to vary what volumes are, of course, but it'll be equal volumes of 100.0 mils of each of 0.100 molar acetic acid and then 0.105 molar acetate ion. Now you'll notice that this is acetic acid, CH3COOH. This is the conjugate base here, CH3COO minus, if you like, AH and A minus. So I may just do that just for kicks. Oops, I did not mean to do that. There we go. do this one. All right. So just for complete clarity here, we'll have AH is equal to CH3COOH. A minus is equal to CH3COO minus. All right. Does anybody have any questions so far? So 100.0 mils of each of these. You'll notice they're the same volume, but they're not quite the same concentration, but they are close in concentration. So this will make up a buffer solution. Our first step here is to find the pH of the buffer solution. On the test, well, actually, since we're doing different kinds of testing, but on the test, if it was a paper test, I'd actually give you that and only make you figure out what the pH is after you've added strong acid or strong base to the solution. So this is the main part here. The 5.00 mils of 0.200 molar sodium hydroxide is added to this solution, which is the buffer, to give a total of 205.0 mils. So I think that makes sense that you've got 205.0 mils of solution because you had 100.0 mils of each of AH and A minus, and you add those together, that becomes 200.0. And then you add 5.00 mils, that becomes 205.0 mils of solution. And what is the new pH of this solution? Now, since we're changing the volume so much during this process, what makes sense is to figure out the number of moles when we get to step B, and that's what we'll be doing. But step A, the first thing we're going to do is try and figure out the pH of just the buffer solution before anything gets added to it. So let's look at the situation that we're dealing with here. So the actual equilibrium that we're interested in is the one that is between actually, let me, I'm going to just use AH and A minus here because it'll be a little bit easier as we go, I think. I won't have to write so much. Let's try that again. So remember what AH is. AH is just the CH3COOH. So AH gives A minus plus H plus. So that's the equilibrium we're dealing with. I'll make an equilibrium. I'll put two arrows here. So initially, we're going to have a certain concentration in molarity of AH and A minus, and we've got here, I've got 0.100 divided by 2 and 0.105 divided by 2 initially, with 0 H plus in the solution. At equilibrium, what's going to happen is we're going to lose all of the AH. And we're going to gain a bit more A minus. That's why I've got the minus Z on the AH side, the plus Z on the A minus side, and then we gain Z moles or Z molar of H plus. Now, let me talk about the 2 here, divided by 2. So remember what we did here to make this buffer. We have 100 mils, or 100.0 mils. And this is the AH. And we have 100.0 mils. And this is the A minus. And then what we've done is we've added them together to produce a solution that is now 200.0 mils that contains both AH and A minus. This is how we made the buffer to begin with. Now, because of that, you'll see that what's happened is for each of these, they've been diluted. They've been diluted to double the volume that they were previously, which halves the concentration. Hence, V divided by 2 here for each of these concentrations. Does anybody have any questions? Actually, let me make that 0.105 divided by 2 as well. Does anybody have any questions about where the divided by 2 comes into play here? Okay. Now I've used delta in the example here for Z. You can use Z, you can use delta, you can use whatever you like. We've been using Z, so I'll just go ahead and use Z. But you know, just understand that I have used delta here as my variable for the Z. Now let me make sure you understand what's going on here with the minus Z as well, and the plus Z and the Z. You see, when initially we don't have any H plus in the solution, but what will happen is some of the AH will break apart into A minus and H plus. So the initial buffer might look like this. So this is initially, where all we have is just AH and A minus. But at equilibrium, some of that AH will break apart into A minus and H plus. So you'll notice that we're going to lose some of the, oops. We're going to lose some of the AH. And we're going to gain a little bit of A minus. So for every AH we lose, we gain an A minus. So that's why it's minus Z on the AH and then plus Z on the A minus and Z on the H plus. So if we lost, say, 15 AHs, we'd gain 15 A minuses and gain 15 H pluses. Does anybody have any questions about this? That's where the minus Z and the plus Z's come into play. I can't believe nobody has any questions about it. All right. Okay, so let's see what we have to do next. We've got to solve for this Z here because Z will be the concentration of H plus in solution, which is kind of what we're trying to find anyway. What slide are we at here? Now, because buffers are made from weak acids by definition, we don't actually have to validate any assumption we make that relate to it being a weak acid. But the consequence of all of this is that we can assume, because it's a buffer and buffers are made from weak acids, so we assume weak acid. And we're talking about AH here as being the weak acid. And like I said, we don't have to validate this, but 0.100 divided by 2 minus Z is going to be 0.100 over 2. So the Z here is so small relative to the 0.100 over 2 that it may as well be that we're just dealing with 0.100 divided by 2. The same thing for the other one. Plus Z is also going to approximate out to 0.105 divided by 2. And that's going to greatly simplify our calculation. So we know that Ka is equal to A minus times H plus over AH. And now we can substitute in all those values. The Ka is something we were given in the problem. Let's go back to the problem here. You'll see that the Ka is given to you along with the reaction. So you don't have to solve for that. You're given that. And that's going to allow you to do this to begin with. So be 1.80 times 10 to the negative 5 is equal to, now we've got our A minus, that's 0.105 times Z, which is the concentration of H plus, over 0.100. Oh, so it should be divided by 2 in each case. Okay. You'll notice that the divided by 2's don't end up mattering anyway because they end up cancelling. But the Z here will come out to be 1.71 times 10 to the negative 5. And the Z is actually equal to the concentration of H plus, or as I've got on the slide, H3O plus. So that's our H plus concentration. Now the pH of that is equal to the negative log of the hydrogen ion concentration, which comes out to be 4.767. Now for sig figs here, we have 3 sig figs, which means we need 3 places past the decimal on the log. That's why it comes out to be 4.767. Does anybody have any questions? So our pH for our buffer, our initial buffer, is 4.767, and this is going to be our reference point for the next part, which we're expecting, since we're looking at the, let's go back to the initial question here. We're going to be adding a small amount of strong base, sodium hydroxide. So what I'm expecting is that initially my pH of the buffer is 4.767. I expect my new pH to be a little bit more than that, but it'll definitely be under 5. That much I can guarantee. Does anybody have any questions? Okay, let's go take a squiz at the method now for solving part B. Now, because we're changing volumes here, because we're first of all going to have the buffer, and then we're going to be also adding a small volume of strong base, it's going to be imperative that we work with moles and not molarities. The moles of things don't tend to change in solution. It's going to be the molarities that change because of the changes in volume. So this is why it's going to be important for us to make sure we convert into moles. So let's go through and we'll start from the beginning here. And I'm going to split this into a few parts. And it's like my psychiatrist told me. I told him I was afraid of stairs. And you know what he said? He said, take it one step at a time. And that's what I'm going to ask that you do here as well. So we're starting out here with the moles, and I'll say initial moles is what we're looking at here. So initial moles. Now to get moles of anything from a concentration and a volume, you multiply them together. So that's what we're going to do first. We're going to find the moles of AH before the addition of the acid or the base. In this case, we're adding base. And then we're going to find the moles of the A minus before we add anything. And then we're going to find the moles of the NaOH that we're adding. So let's go to we'll go to the next slide here. And you can see this. So this is initial. Now, just for simplicity's sake, I'm using AH and A minus here. So the initial moles, so moles of AH, is going to equal 0.100 moles per litre times 0.10000, sorry, 100 litres. And that gives us 0.0100 moles. Now you might be wondering, well, where's that 0.100 litres coming into play? 1000 litres. Well, that's coming from, if we go back to the question, the fact that we started out with 100.0 mils of each of the AH and the A minus. And what I've done there is I've taken those 100.0 mils and converted them directly into litres. Now, if you wanted to, you could show the conversion and everything else, but you notice I have preserved the significant figures as well, because that has 4 significant figures and 0.1000 has 4 significant figures too for the litres. And then when we do the math here, we end up getting 0.0100 moles. That's 3 significant figures because we had 3 significant figures here for the concentration. Does anybody have any questions so far about those moles? So we're going to also do the moles of A minus as well. And if you look at the problem there, it's going to be 0.105 moles per litre times, and again, the same volume, 0.1000 litres. And that comes out to be 0.0105 moles. Now we also need the moles of OH minus that we're adding. And again, we do a very similar thing for that. We've got 0.200 moles per litre. And we're going to multiply that by the volume we're adding, which is 5.00 mils. 0.00500 litres. And that comes out to be, you'll see this over here in the slide, .00100 moles. Now, it's important to note that the amount of OH minus that we're adding is less than the amount of AH in the solution. Do you see that? It's 0.00100 moles, whereas the moles of AH is 0.0100. So there's about 10 times as much AH in the solution as we're adding OH minus. Now, this is important because if the OH minus was more than the AH, it would mean that the buffer would be completely overrun and we would end up getting no real small rise in pH. It would be a massive bump in pH because the OH minus would eat up all the acid. But you'll notice it's less, and that's important here. So I'm kind of telegraphing what we're going to do next. And this is kind of the key step to the whole thing. So I'm going to go show you a picture here, and it's kind of something I alluded to earlier. So I want you to focus here on the right-hand side where we're adding the OH minus to the solution. So we've got our buffer here, which is a combination of AHs and A minuses. So this would be initially, you could say, we add in an OH minus, and because of the reaction I showed you earlier, and I'll put that reaction down here, the AH plus the OH minus here will lead to A minus plus H2O. But what's important to note is, of course, that we don't have as much OH minus as we have AH. So the AH is initially 0.0100 moles. And the OH minus is, of course, 0.00100 moles. So there's a lot less of that. So I'm hoping that you can see how much A minus we would get from that. It would lead to 0.00100 moles. Actually, I'll do this as a separate part here. Sorry about that. So this will be initially. Then this will be after reaction. We'll end up with, actually, I'll do the A minus first, which is going to be 0.00100 moles. There'll be 0 OH minus in solution after this is reacted. And here we'll have 0.0100 minus 0.00100 moles. So the whole point of what I'm trying to get at here is that we are gaining A minus, and we gain as much A minus as we add OH minus, but we also lose that same amount of AH as well. So that's why we're doing this subtraction step here, which is really the key to what I'm talking about. So I'll go back here to the method that I was showing you earlier. And this is the step we're at, step 4. For sodium hydroxide, we need to find the number of moles of AH. And we do that by subtracting the amount of OH minus from the AH. And that's what I'm doing here. And for the NaOH on the A minus, we add. So whatever we have here, we add. Okay, so I'm just giving you some ideas here about what's going on. I'll get rid of that. So this is what I'm going to call the reaction moles. And they'll take questions after this. Okay, so this is reaction moles. So the moles of AH will equal the initial moles of AH minus the initial moles of OH minus. And this is what I was talking about earlier. So it'd be 0.0100 mole minus 0.00100 moles, which comes out to be 0.0090 moles. The moles of A minus, those will go up. That'll be the initial moles of A minus plus the moles of OH minus. And that's going to be 0.0100 moles plus 0.00100 moles, which comes out to be 0.0110 moles. So what are we looking at there? And this is the key step that I'm trying to get at here. We've got a minus, and here we've got a plus. And all of this comes from this diagram here, where you can see that by adding OH minus, the AH goes down, and you can see that the A minus goes up. The AH goes down by as much OH minus as we add, and A minus goes up by as much OH minus as we add, which is why we've got the minus and the plus here. If we were adding strong acid, H plus, the reverse would be true. This would be plus here on the moles of AH, and moles of A minus would be minus instead of plus. So that's going to be the difference between adding strong acid and strong base to the buffer solution. Does anybody have any questions?
I do. I just want to make sure I'm following along correctly. At the end there, where we're calculating the moles of A minus, I think we started off with 0.0105.
Oh, okay. You're right. Sorry, you're right.
I just don't want to be confused. It's
Sorry.
okay.
Thank you. You know what? I made a mistake here. It should be 5, and that should be 5 down here. I'm sorry. Okay, I'm going to let me correct that. I'll actually erase it. It's a good thing about this. I can use my little eraser here. We can make sure that that's right. Thank you, Kyle. I had forgotten that. It's 0.0105, and this would be 0.115.
No, it's okay. And earlier I forgot that's what the number was, and I thought, so I was like wondering where you got it from, and now I'm good.
Okay, so you can see here, this is worked out here on the slide here as well. So we've got the 0.0090 for the AH and the 0.0115 for the A minus. Thank you. So that's what I'm calling reaction moles and initial moles. Now I'm going to open another file here, so I can leave the other one there. I'll see if I can get a little bit clever about this and shrink it a little bit. Okay, there we go. So we can now work on the concentrations, and these are the concentrations in the final solution once we've added the sodium hydroxide. So we have the concentrations, any concentration we deal with is going to be moles divided by volume in liters. So for the AH, the concentration of AH, it's going to be 0.0090 moles divided by 0.2050 liters. All right, so let's talk about where we're getting that from, the 0.2050 liters. If we go back to the initial problem, we're actually told that the total volume of solution at the end after we've added the 5.00 mils of sodium hydroxide is 205.0 mils. We get that from 100.0 mils of each component of the buffer to give 200.0 mils, and then the extra 5 that we're adding for the sodium hydroxide. So that's where that 0.2050 comes into play. So the concentration we're looking at there is going to be 0.044 molar. For the A minus, it's going to be 0.0115 divided by 0.2050 liters, which comes out to be 0.0561. So this is how we're getting the final concentrations of the AH and the A minus that we're going to end up using in the final step. Does anybody have any questions at this point about what we're doing? So now we can do what we did previously. And we can figure out what the concentration of H plus is going to be in this final solution. So again, we have our equilibrium here, which is A minus, AH going to A minus and H plus. Excuse me. Now, understand at this point, we don't have any H plus from the dissociation of the AH, which is why we're doing this now. So the AH has an initial concentration of, let's see, 0.044. The A minus is 0.0561. The H plus is 0. And at an equilibrium, based on the logic I presented earlier, we lose a little bit of AH and we gain a little bit of A minus. So plus Z and Z over here. Now whether we added strong acid or strong base, this minus and plus here don't change. And that's kind of a mistake that people often make. Let's see, so Ka is equal to A minus times H plus. This will allow us to solve for the H plus and get the pH of the buffer solution. So the A minus here is 0.0561. Oops, I did forget one step here. We assume it's a weak acid. So 0.0444 minus Z is going to approximate out to 0.044. And the 0.0561 plus Z will approximate out to 0.0561. So again, we substitute those in. And the Ka value is what we were given at the beginning, 1.80 times 10 to the negative 5. And the Z value here ends up being 1.4 times 10 to the negative 5, which happens to equal the concentration of H plus in the solution. And the pH then is 4.85. Now this one only has 2 significant figures for Z, so we end up getting 2 decimal places on the pH. So the whole point of this is that if we go back, we look at what we did for the buffer. It was 4.767. That was just for the buffer before we added anything to it. And then at the end, it went up a little bit to 4.85, so about 0.07 of a pH unit, because we added some strong base to that buffer. Does anybody have any questions? So again, summarizing the steps that we did, and we'll focus on the sodium hydroxide here. We found the moles of each of these before we added the sodium hydroxide. So the moles of AH, the moles of A minus, and then the moles of OH minus we were adding. The sodium hydroxide, the number of moles of acid goes down. That's going to be moles of AH minus, moles of OH minus. So step 1 minus step 3. And then for the A minus, it goes up. So it'll be step 2 plus step 3. So the A minus, you add the OH minus to it. We find the concentrations by dividing by the total volume in liters. And then we find the delta or Z or the H plus here in order to be able to get the pH of the buffer solution at the end. That's what we did. Does anybody have any questions? Does anybody have any questions? All right, let me show you something else here. I'm not actually going to write out all the math here, but I will show you something. In the buffer folder, I have a document called Buffer Problems, which I'll download here. And what it's got is it's got 2 worked examples. The first one is the one we've already done. It goes through and shows you the same working as what we just did for question number 1 here. Now for question number 2, it shows you what happens and works through if we add here 10.0 mils of 0.150 molar HCl, right? So remember in this first one, we added 0.200 molar NaOH. In this one, we're adding 0.150 molar HCl. So we go through, we're going to do the same steps. And I have the steps here. And you'll notice, and I'm going to focus on the reaction step here. When we're doing the moles of AH, we add the moles of HCl. So if you look back at the previous example here, where are we? You'll notice that to get the moles of AH, when we added the OH minus, we subtracted. And here, we're adding. We add the moles of HCl. And then to get the moles of A minus, we subtract moles of H plus. Now the reason for that, and I'd ask you to focus now on the right side, is that when we have A minus, it reacts with H plus and forms AH. So we end up having AHs go up and the A minuses go down. So it's going to be the reverse of what happens when we add OH minus to the AHA minus solution, where the A minuses went up and the AHs went down. So that's the only thing that changes, this plus and minus here. Does anybody have any questions? Anybody have any questions? I know it's a fair amount to go through. Yeah, sorry.
So how, like in the question of the problem, would you know what to plus and what to minus?
Because you are always told if you're adding sodium hydroxide or HCl, NaOH or HCl. So you do it depending upon what you're adding.
What you're adding? Okay.
Yeah. All right, I'll point out one other thing as well. Let's go back down here. Sorry, gotta find where I'm at. Is a step here, okay. So this is the one that we have on the slide is adding sodium hydroxide. You'll notice at the end here, it was 0.044 minus delta or Z, and then plus delta. You'll also notice that we do exactly the same thing here. Even though we added HCl, we still have minus delta and plus delta here. So it's important to note that at equilibrium, since the HCl and the sodium hydroxide are now gone at this point, I'll say it again, the sodium hydroxide and the HCl are gone at this point, then the minus and pluses here don't change. We have them both the same in both examples. So that's important to note as well. All right, let's take a look And Georgiana, I'm actually going to go through some of these problems now. Let's look at the fun quiz first. We'll look at the buffers practice quiz. No, I won't do that yet. No, I'll go back to test 2. I'll go back to test 2, then I'll come back to the buffers practice quiz. So I want to focus now on the actual problems that you'll see on the ungraded copy of the test. And they'll be under the heading of buffers. Here we go, starting at buffers here. So starting at question 16. So a buffer is made up of equal volumes of 512.2 milliliters of each of 0.789 molar AH and 0.890 molar A minus. We're adding this much HCl to the buffer. How many moles of A minus are present after addition of HCl? So what we're doing here is just that first step here of figuring out how many moles we have of each in the solution. So I'm not doing the whole problem here, just part of it. So I will go through and show you that. Now remember, I do have videos for all of these as well, all these specific problems on the test. So don't forget about that, because that can be helpful too, especially if it's been a while since you looked at it. It can be a really good reminder of what you need to do to continue with something. Okay. And it does ask for the correct significant figures here as well, so that's going to be important too. Okay, so we have a buffer of 512.2 mils of each, and it's 0.789 molar. I'll just draw a picture of this because it can be helpful, I think. Sorry. Here we go. So these are both 512.2 mils. And we also have the concentrations of each. So this would be AH, and this one's going to be A minus, and this was 0.789 molar. And the other one, oops, yes, that's right, is 0.890 molar for the A minus. And these are initial. And we're adding, so we're going to put those together. And then we'll add in H plus, and the H plus is going to be a portion. I'll put this in a small beaker here. 15 point, so these two get added into this big container. Then we'll have 15.31 mils of the H plus, or which comes from the HCl. And we have a molarity of that as well, of 0.399 molar. So what we know is that the H plus won't react with the AH, but it will react with the A minus. So what's going to happen is that and what we're looking at here are how many moles of A minus are present after the addition of HCl. So we know that the A minus is going to react with the H plus to form AH, which means the A minus is going down. See, in this buffer solution, that's what we've got is AH and A minus. The A minus goes down, which means that the new A minus is going to be the initial minus, in moles, we'll say moles, minus the moles of H plus added. Okay, I'll stop here for a second. Does anybody have any questions? You're all fine with that, huh? Nobody has any questions about this? All right. So the initial A minus moles is going to be 0.890 moles times the volume that we had, which was in liters, 0.5122 liters. And that's going to be minus the moles of H plus, which is going to be, and I'll put this in parentheses, minus 0.399 moles times the amount we're adding, which is 0.01531 liters. And that'll give us our answer. Does anybody have any questions? Nobody has any questions, huh? All right. Question 17 is similar, but now it's asking for the moles of A minus that were added after the addition of sodium hydroxide. So I'm going to just modify this a bit. I'm not going to redraw the whole thing here. Okay, so the situation here, we have 0.874 molar on the AH. We have 0.731 on the A minus. The volumes, 369.2 mils. That's for each of them. And the OH minus that we're adding is going to be 0.580 molar and the 6.00 mils. So here the situation is that the AH is reacting with the OH minus that we're adding and is becoming A minus plus H2O, which means that the A minus is going up. So the new A minus is going to be the initial moles of A minus plus the moles of OH minus that we're adding. So that's going to be 0.731. Molar times the volume in liters. And that's going to be plus the amount of OH minus being added, and that'll be the moles. So it's important here, you know, with these two questions, both 16 and 17, to be aware of whether you're adding or subtracting. And these are going to vary. It could be any one of four possibilities here where we're adding HCl or sodium hydroxide, and we could be looking for the AH or the A minus. I know here they're both A minus, but you could also be looking for the AH as well. And you need to be aware of whether you're subtracting or adding, and that can be that can take a little time to get straight. All right. Does anybody have any questions? And that gives an answer, of course.
Just with significant figures, those would be 3 then, because of the molarities?
Yeah, the molarity, well, you get 3, you'll have 3 significant figures on the multiplications. And then that would be, then you'd have to have the right number of decimal places because we're adding at the end here. So you'd have to take account of the sig figs here at the beginning, and then add the then when you do the addition. So let's see. I'll answer that. Let's see, 0.731 times 0.3692. 0.270 is what I get here. Plus, and I'll do the other one. .00348. And you can see that the answer then would have to be 0.273 because of the decimal places. So 3 decimal places, 5 decimal places. So it comes out to be 0.273.
That's what I got.
Yeah. But not 3 significant figures necessarily because so much of the, because you have to make sure you get that.
It's because of the addition, subtraction at the end.
That's right. Yeah, that's really the key there. But you're right, it did end up being 3 because of that, but not because of
Got lucky.
Yeah. All right, any questions? Any questions? Okay. Now question 18. Let me expand this out a bit. This is the table that we get while we're doing that. And I'm going to give you a spoiler alert here. Whether we're adding sodium hydroxide or HCl, the right answer doesn't change. So it is kind of a trick question, but that's the whole point of it, is to make you realize that whatever table you pick will be the one that is going to be the same regardless of whether you're adding HCl or NaOH. I'll leave that to you. The last question here, it makes you go through the whole process and figure out what's going on with the whole thing by basically giving you the same kind of questions we had on the test. So a buffer is made up of equal volumes of AH and A minus. It gives you the molarities here. It's after the pH of the buffer, after addition of 6.86 mils of sodium hydroxide, and it gives you the Ka here as well. So that just makes you go through that entire process that we just went through on the PowerPoint slide to come up with your answer, which again, it comes out to be a pH. pH doesn't have units. So you just go ahead and put that answer in there once you get it. Does anybody have any questions? So those are all the buffer questions that you're going to see on the test. Are they easy? Well, not initially, no. But once you get into it and you practice them a bit, you'll find it's not really as bad as it seems. That much I can promise you. I know it seems really bad right now, but it actually isn't nearly as bad as it looks. I'll show you the buffer problems in the extra credit. Now these are, I admit these are tough. I'm not going to mince words with you. This is a tough exercise. I'm not going to deny it, but it is extra credit too. So I've always believed that I can have my extra credit as tough as I want, really. You really can't complain because it's extra credit. You don't have to do it. So a buffer is made up of equal volumes of AH and A minus. It gives you the molarities here. We add a certain amount of, in this case, NaOH, but you can see that we could be adding HCl as well. So you've got to be mindful of that. And then what it's asking for is, by what amount will the pH change? So a negative value indicates a decrease and a positive value indicates an increase. So for this one, you're going to have to figure out the pH of the initial buffer solution, and then you'll have to figure out what the pH is once you've added the sodium hydroxide, and then find the difference between the two. So that's fun. That's fun as well. All right, so that was the main stuff I had wanted to go through today. Does anybody have any questions? Anybody have any questions? I want to remind you, because I'm not sure everybody is aware of this, but I want to remind you, go back to the quiz here. Go back to the test 2 folder. So you've got the ungraded copy of test 2. And then underneath it, you've got the practice test 2 videos, which goes through every single problem type that's on the test here. And it tells you what the possibilities are as well for each of those. And it goes through every single possibility too. So question 16 to 17, I told you it was a choice of 4 possibilities. These are all the possibilities. So I haven't been lazy about this. I've actually shown you all the different possible ways that the question could be asked and given you videos for each of them. You know, I could have been lazy and just put down 2, but I didn't. I didn't. I went through, I did the hard yakka, as we say in Australia. Hard yakka, did the hard work and put down all the possibilities here. All right. So does anybody have any questions? Anybody have any questions? All right. Well, yeah, I guess we'll leave it there for today. I think we've worked hard enough today. I feel like I have. That's for damn sure. All right. If you want to hang around and talk to me, you may, of course. But in any case, I'll see you later.
See ya.
All right.
Thank you.
Bye.